Thomas Reed in 1786 said that a chain is only as strong as the weakest link. At Systech, we consider an air pollution control system a chain of 7 key links or components. More than a group of scattered pieces of equipment, but a system of carefully selected components that function together. If one component is weak or incorrectly applied, the system design will most likely be compromised. The first C is capture. Our goal is to collect 100% of the pollutant while minimizing the amount of ambient air required to entrain the pollutant. That can be difficult due to the process layout, building cross drafts, negative or positive room pressure, and worker access or machine design. The less air we capture, the smaller the system horsepower, duct diameter, and dust collector size. A capture hood may be a simple scoop design, a multifaceted hood design for hazardous pollutants or potent compounds, or an entire room enclosure. Our video shows an enclosure mounted above a scrap metal melting pot with access doors on tracks, completely encapsulating the process. The doors on the hood are closed during the melt, reducing the in-draft velocity needed for containment while reducing horsepower and collector size. Conveying is our second C. Duct diameter and airflow need to be designed with a carrying velocity to keep the captured pollutant in suspension. The lower the duct velocity, the less friction loss and required horsepower. At the same time, hood entry losses, branch entry losses, and elbow losses need to be considered. Again, the lower system pressure losses, the lower horsepower requirement, and both capital and operational costs. The third C is clean. Now that the dust or pollutant is in the dust collector, we need to filter the particulate from the airstream and have it fall into the discharge hopper, while at the same time reconditioning the filter media for continuous duty service. We are showing a compressed air pulse clean cartridge dust collector in our video, which is the same cleaning system used with polyester bag and pleated bag style dust collectors. Effective reconditioning of the filters is dependent upon both filter media selection and the design of the compressed air pulse system. Filtration efficiency and surface loading along with release characteristics of the filter media will determine the life of the filters and future maintenance requirements. The next or fourth C is conveyor. Conveying the particulate from the hood through the duct into and out of the dust collector requires a properly selected exhaust fan. The fan is the heart of the entire system, and a thorough review of the fan efficiency and performance curve is essential. A centrifugal fan with a backwardly inclined or airfoil wheel is a desirable choice. If we couple fan selection with a variable frequency drive, we can expect significant energy savings, lower noise, and reduced capital cost. Direct-driven fans with a variable frequency drive are 30 to 40% less costly than a belt-driven fan with an outlet damper and motor starter. The fifth C is controls. In addition to controlling the fan motor through a variable frequency drive, the panel should include pulse cleaning controls and system diagnostics. Cleaning the filters only when required extends the life of the filter media. Furthermore, simple controls with touchscreen diagnostics minimize maintenance requirements. The sixth C is components. There are many optional components to an air pollution control system such as fan silencers, rotary airlocks, compressed air filters, and flex connectors. A frequently misapplied component is the fan noise attenuation. Typically, the rule of thumb used for fan attenuation is an 85 decibel silencer for an industrial environment. However, given the fact that noise is logarithmically added, selecting a silencer with a design of 85 decibels might not meet plant mandates. For example, adding 2 noise sources with the same decibel value increases the combined decibels by 3, or in this case, 88 decibels. You need to be aware of other noise sources in the room or area along with reflective wall surfaces to ensure the entire space remains compliant with OSHA regulations. While on the subject of noise, use of acoustic flex connectors is a requirement. Light-duty rubber flex joints offer little noise attenuation and will add breakout noise into any room. The final and seventh C is containment. Handling of toxic or potent compounds necessary in some pharmaceutical facilities includes features to curtail exposure of the employee to the particulate or compound. The dust collector body is fabricated to have a higher specification. Associated equipment includes bag-in, bag-out filters, double valve bag-in, bag-out hopper discharge, and bag-in, bag-out HEPA filter assemblies. Since we've published the 7 Cs, there has been a firestorm of activity around code compliance related to fire and explosion prevention, and protection as dictated by NFPA and OSHA codes. Where fire is a potential issue, prevention and protection options include spark detection, extinguishing systems, use of abort gates, and CO2 systems. In addition, where combustible dust explosion is a concern, prevention and protection options might include explosion vents, chemical suppression systems, and isolation valves. Our video illustrates an explosion protection option which includes a chemical suppression system, explosion vent, and a chemical isolation bottle to prevent a fireball from going back into the facility. Because every application is different, it is essential that you speak with a specialist about your explosion protection and suppression needs. Having your dust tested is a good starting point for determining your facility's needs. The expense associated with this test is minor compared to the potential cost and impact that an explosion would have on your employees and business. That's it, the 7 and soon to be 8 C's of a pollution control system.